Hi everybody, thank you for joining us for our latest Tech Talk. Today's Tech Talk is about avoiding potential mistakes when you're working with carbon fibre, especially on the application side. I'm Steve Musa, one of the project team. I'm joined by my technical director, Jayesh.
Hello everyone.
So let's jump straight into it, Jay. We're looking to avoid potential mistakes. So I think the first question we're going to be asking, why would you look to use carbon fibre in the first place anyway?
Yeah, so carbon fibre is a very high strength and lightweight material which is becoming quite popular these days. Pretty much all the structural engineers, contractors, architects are looking to use it because, as I said, it's very high strength. So just to give you a feel in terms of number, it is at least 3 to 4 times stronger than steel. It is 7 to 8 times lighter than steel. So you could see strength to weight ratio and why people prefer to use FRP over traditional methods. Also, it can be used on strengthening concrete structures, steel structures, wrought iron, cast iron, even the timber structures. So you can strengthen pretty much all type of structural construction material using FRP.
And a bit of a misconception, I think, as we say, is that a lot of people think it's a new form of strengthening, but that's not the case, no?
No, it is not. But as compared to concrete and steel, it is still a new technology.
Yeah.
So for that reason, people think it's a new material, new technology. But this was first used in aerospace engineering in 1944. And they started making all the aeroplanes, fiber boats using FRP. Then in 1988, this was first used in construction. So it's at least over 30 years old technique which has been used in construction.
And because of its low profile, something that you mentioned earlier, the architects really do like using carbon fibre.
Yeah, so the typical thickness of one layer of carbon fibre is around 1 millimeter. So imagine if you're able to strengthen a beam, column or a slab with one layer or even multiple layers, you're increasing the dimension of the element by a few millimeters, which is negligible in overall scheme. And that is the reason architects prefer to use it, because obviously you're not changing the shape and size of structure significantly.
So architects love it for its low profile.
Yeah.
Main contractors now go to designers asking them for a carbon fibre solution, purely on the economic side. Why is that?
Yes, so it is, as I said, it's very high strength and lightweight material, but to apply this, it takes very less time in application. So they save a lot of time in their program.
Okay.
For that reason, they are going to the structural designers that can you look into carbon fiber. But what happens usually is that people just compare the cost of carbon fiber material with the cost of steel or concrete only. And in that case, they may find it expensive. But in reality, when you see the whole cost in terms of material, labor, disruption to your structure, and most importantly, time in doing that strengthening, then carbon fiber is the most economical solution available in the industry at the moment.
Okay. So avoiding potential mistakes, let's go into the design side a little bit more then, Jay.
Yeah, so in terms of the design, there are some mistakes designers have made in the past and still you come across them. So this is a stress strain behavior which shows the behavior of both carbon fiber and glass fiber, and that is compared with the steel. So what happens that we all know the behavior of steel. There is a yield stress. We design steel based on the yield stress. So we need to carry a force, or design steel for a force. We divide that force with the yield stress of the steel we are using. That is give us the area of steel required to carry that force. In CFRP design as well, people take similar approach. So they take the tensile stress given on the data sheet and then use that tensile stress to calculate the FRP. But that is not the correct way. The reason for that is we can see on this stress strain behavior that carbon fiber, glass fiber, or any FRP for that matter has a linear elastic behavior until they fail. So there is no yield point or no warning before a brittle failure in the FRP.
Okay.
So for that reason, FRP design will always be a strain limit design. So how do we approach the design is that we only use the modulus of material and the thickness of material from the data sheet. Then the strain is derived by us or by the designer depending on the guideline they are using and also the type of strengthening they are doing. That will give them a strain value. Then that strain value is multiplied with the modulus from the data sheet. That will give them the tensile stress or design tensile stress for the FRP, and that stress should be used to calculate the area of FRP required for a particular force. So again, I'd say it's a strain limit design. You should always design it based on the strain limitation depending on the guideline you're using, and should never just use the tensile stresses given on the data sheet, because those are ultimate tensile stresses.
It's a critical point. And with regard to glass fibre itself, generally speaking, where would you look to use glass fibre as opposed to carbon fibre?
Yeah, so on this curve we could see that carbon is stronger than steel and glass is better deformability or ductility, if you like. So if we are strengthening a structure for expected movements, for example earthquake forces or a vehicular impact on a central reservation columns or something like that, in that instance we use glass fiber because we are looking for ductility in the structure. Otherwise we generally use carbon fiber, where we are just looking for pure strength out of the structure.
Okay.
The other common mistake made by the designers in past was, especially whenever they are using a fabric or wrap system, they design it based on dry fiber property, which has been done in past as well, because they use the dry fiber modulus, theoretical thickness, and then that's how they design it. But technically it's a composite material. There are at least two materials mixed together to make FRP. So there is a fiber which is mixed with epoxy matrix. When it cures, it becomes a laminate. So in the design we should always consider those final cured laminate property and not dry fiber property. And that is another mistake which people have made in the past, so that we should be aware of that, especially the fabric system needs to be designed based on final cured laminate property, because that is the property you're going to get on your structure.
Okay. So we're looking at a key area of using anchors, and we've sort of brought this to attention because we believe that certain projects or certain assets that are being strengthened, anchors aren't being used.
Yeah, so most commonly people, whenever they're strengthening structure for hogging moments or something like a beam strengthening or slab strengthening, the first material they come across is carbon plate, CFRP plate or pre-cured carbon fiber plate.
Yeah.
Now, because that's already cured, there is very limited thing you could do with that. So especially for hogging moment strengthening, what happens usually is that you take the FRP up to the end or support, and then you stop it there, because there is no way you can continue beyond that point. And also plate can't be bent on site. So even in fabric system as well, people take the FRP and stop it there. But we know that that's the location where we have the peak stress, and we should never curtail the reinforcement at the requirement of the peak stress. And this is not just for the FRP, even it is for traditional reinforcement as well, that we need to have a development length or anchorage length beyond that point. Now that is done using carbon fiber anchors, or you can, if you're using a fabric system, you can go up the column, then wrap around the column using additional layers or something. So there has to be some sort of anchorage detail provided there. You cannot just stop it there, because if you are, then technically your FRP is not effective at that point. It will be effective few 100 millimeter inside the span, because the end through 200 to 300 millimeter will be treated as an anchorage length. The other thing is that use of these anchors in shear strengthening. So usually shear strengthening is done like, imagine putting like a link or a stirrup from the outside of a beam.
Yeah.
That's why it's called U-wrap strengthening. So again, in that as well, obviously you cannot use plate system there, so you will use fabric system. So what people do is they just apply it like a U-wrap. But again, if you use these anchors, drill a hole between the beam and slab junction, put these anchors diagonally like that, they provide similar effect as in closed.
So this is the diagram shown on the left, yeah?
Yes, it is, yeah.
Okay.
Now these are the some of the images of these anchors, which show the use of these big super anchors, which are specially designed anchors. So generally a nominal anchor or a blind anchor, as we call it, in which we are not going all the way through the element, is working as we drill a hole into the concrete, we saturate the anchor, put half of that anchor into that drilled hole, which is filled with epoxy, split the remaining half on face, which we already would have one layer applied or other layers applied there.
And this is the diagram shown on the far right, yeah?
It is, yeah.
Okay.
And then we put one more layer on top of it, so it will become one unit which will cure simultaneously, but it is actually going into concrete.
Yeah.
So it provides you additional anchorage or bond capacity, so your debonding or delamination failure will not happen. So these kind of smaller nominal anchors are used mainly for construction detailing or for shear strengthening. But then there are these specially designed anchors which are called super anchors.
And that's a picture shown
in the middle,
the center of the guy's holding,
So they are specially designed anchors. They'll be designed for a particular force.
Okay.
So the design of them, the size, diameter, everything will be derived at the time of design. And the use of them is shown in the pictures on the right hand, on the left hand side. So the top and bottom image, you could see the bottom image is basically slab strengthening. So in that case, there was an obstruction in the way. There was a column in the way. So we were strengthening the slab on top. there was column in the way. So what we did was that we drilled hole through that column, used these bigger and longer anchors, pass them through that drilled hole, splay them on both sides so they covered the full width of FRP or the column, and then put one more layer on top of it. So after curing, these anchors become as a tie, which is transferring force from one side to another side. In other words, we've got a continuous top reinforcement at the location of column. So that's the way these anchors are used. And similarly, the image on the left hand side, the top image, is basically showing strengthening of a shear core, in which we strengthen the vertical element but use these anchors to transfer strengthening between the floors. So the holes were drilled through the slab to connect the strengthening on floor above to floor below.
Just a matter of interest, what was that project? It was quite a big project at the time.
Yeah, that is a London project, Hill House it is. So there was an existing 11-story structure. They added additional 4 stories on top of it. So the shear cores needed additional reinforcement for new wind load. So for that reason, the whole shear cores were strengthened from 11th story to the basement.
Wow.
And at every slab level, these anchors were used, and ultimately everything was anchored into pile cap.
Okay. So the preparation, application and testing, absolutely critical to the whole process as well.
It is, yeah. So FRP design is one part, so there are a few mistakes which should be avoided in the designing of FRP, but even in that as well, you've designed it, as well as you want. If it is not applied correctly on site, it is not going to work. So for that reason, the application is the key part in any FRP strengthening scheme, and for that reason, we do not subcontract it at all.
Before we actually start the application procedure, we need to check for humidity and temperature readings, yeah?
Yeah, so these are called bond records. So this is a part of quality assurance and quality control process we have, or every applicator should follow them. So basically what you need to do is that before applying carbon fiber on any area, you should always take these kind of readings just to make sure that the environment and the climate is correct for the application. So we need minimum 4 degrees centigrade temperature to apply FRP. Humidity should be less than 85%. And all these records should be kept for the applications you have done, which could form a part of your O&M manual. So that's the first thing guys have to do. But in winter months, it might not be possible to get that kind of temperature or climate.
Yeah.
So they have to use these kind of artificial heating arrangements. So they can enclose the area, heat the area, get that environment artificially, and then apply the FRP.
So the temperature readings and humidity tests, they're literally done on a day-to-day basis before they start work, yeah?
It is done every day or different times of the day as well. If the weather is changing, they'll take the readings again just to make sure that it has not changed drastically and not, gone below the requirements or something.
Okay. So we'll look at the application process itself then, Jay. So the guys starting her off.
Yeah, so first thing is surface preparation, which is done by diamond grinding. So you grind the area, take the smooth lattice off from the concrete, so you get a key to bond FRP. You will also drill holes for the anchors if you're using anchors in those applications.
This is what he's doing now, though.
Yeah, this is a beam strengthening example for shear strengthening, where they're cutting surface weather penetrations through the beam. So in that case, they're using these holes to put the anchors in to get the full effect as in closed loop. So once that's done, you clean the area, then prime the area using pure epoxy. So that's another thing to note in terms of application. You use pure epoxy to prime the area so that epoxy can soak into concrete and you get better bond. Then they apply first coat of thickened epoxy, which is the white color epoxy we are seeing. So once that coat is applied, they unroll the first layer of carbon fiber. Then put another coat of epoxy, then another layer, and that's how they build up the number of layers. But the other thing which is quite important to note here is that the carbon fiber they are applying is saturated on a different area on same site. So when they're applying it, it's in wet condition. So that's why this application is called wet layup method, and all the fabric application needs to be wet layup method. You should avoid doing dry layup, and it is more or less abandoned now in Europe.
So he's putting in the anchors there now on top of the first layer of carbon fiber, yeah? Yeah,
so you insert the anchor, you'll saturate the anchor, put half of that anchor into that drilled hole, then split the remaining half onto the applied layer of carbon fiber, then put another layer so the anchor becomes sandwiched between layers of carbon fiber, so it's completely covered and will be fully connected with all the FRPs there. So that's how these anchors are used. So once that is done, the final layer is applied, then they apply a final coat of epoxy and then finish the application that way. After the application, if there is a requirement to apply additional coatings such as a fire protection coating or paint coating or something, you can apply that. But to be honest, FRP is good with anything. You can plaster it, paint it, render it, you can do anything on top of it.
So the actual curing time for the carbon fibre to be fully cured is how long?
It is 4 to 6 hours. It will become touch dry in ambient condition, and
Yep.
it will be 100% cured in 72 hours. So you can reload your structure back to its new capacity in 3 days' time. And the other important thing to note is that there are limitations on how many layers you can apply in one day or one shift.
Mm-hmm.
So if it's a vertical or overhead application, you're limited to apply 3 layers. After that, the saturated weight of fiber could result in debonding before its initial setting. So you leave it to become touch dry. So usually what applicators do, they apply first 3 layers on day 1,
Mm-hmm.
then they let it cure, then they come back next day and apply further layers if there are more than 3 layers. But in this application, it was just 2 layers, so everything was done in one go.
So the key area was saying that looking to avoid mistakes in that, but we can, generally speaking, you can tell within a day or so, you can check the carbon fibre for any issues that you may have?
Yeah, so if anything is wrong with the application, you will see air bubbles coming up or carbon fiber debonding or something, and all that will happen within the first few days of application.
If it's not been applied
Yeah,
correctly.
if it is not been applied correctly. Yeah.
Yeah.
But once it is cured, you can do a tap test, and
Okay.
then you can make sure that it is bonded correctly and there is no hollow sound or air bubbles or anything in there. Because if this application is not done correctly, we can get these kind of results where you may have discoloration of epoxy because of the incorrect climate condition in which it was applied.
You can see quite clearly on both of those photographs, and I'd just like to point out these are not our sites. We've had to get the photographs from colleagues abroad, but you can see the air bubbles, or it's not set.
Yeah, so I mean there are air bubbles, there is pockets there. Also, you could see discoloration of epoxy on the left side image. That happened. It's called amine blush in the epoxy. That happens when you apply epoxy in a very low temperature.
Mm-hmm.
So it reacts and all those things, and it becomes in a very different color. So that tells you clearly that it was not applied in correct environment. Also, the air bubbles, the TR57 gives you certain guidelines in how much air bubbles or debonding could be allowed in a certain length of the carbon fiber.
Yeah.
Usually you should not have any air bubbles. So these air pockets, you could either inject them with the epoxy afterwards, or you can cut the patch and put additional layers there. So that's the way you treat with these kind of issues if you come across.
Okay, so we'll go on to the once the carbon fibre has been applied, we're looking at testing and that. There are 2 types of tests?
Yes, so there are 2 types of testing which we do on a real project, and that is something which designers or people who are specifying project
Mm-hmm.
sometimes forget to ask contractor to do. But they should always ask contractor to do a pull-off test on any bond critical application like beam strengthening, slab strengthening. So this bond test is slightly different than your standard concrete pull-off test, because in that we look out for a number in terms of pull-out strength.
Mm-hmm.
But here we are more interested in mode of failure. So after the 100% curing of FRP, we perform this pull-off test from a sacrificial patch on the same area. And all we want to see is that when you do this pull-off test, it should not come out from substrate only, or it should not come out from another layer of FRP if there are multiple layers. So in the middle image, we could see that it took out some concrete with it, and that was an application of around 4 layers there.
Okay.
So this shows that the bond between FRP and concrete is stronger than your actual concrete failure strain. So that's the pass criteria for this. And the second test we should do is, especially for the fabric system, is we should do this composite laminate testing. So when they are saturating the carbon fiber prior to application, they should also create these kind of test plates, which are 300 millimeter by 300 millimeter.
Yeah.
The requirement as per TR55 is to cast 2 plates per roll of the fiber.
And they're made on site, yeah?
It is. They're made on site and they're left on site to cure. And after that, you send it to independent laboratory. They can cast a coupon out of it and do a tensile test.
Okay.
Those tensile properties should match with the data sheet of the material, or should match with your design values. So that's the pass criteria for that.
And we keep this data for the benefit of our design records, and also for the client a specific time?
Yeah, as I said, that most of the time the engineer who's specifying carbon fiber strengthening don't even ask for any tests, but this is part of our QA/QC system where we will do it anyways and we'll keep records of them. So if client or project engineer needs any testing or something, that can be done using these samples.
Okay. Well, that's our tech talk for today. Many thanks for taking time to join myself and Jay. If you want some more information, please go to our website. There's lots of data, lots of video content for you to see. Thank you very much for joining us today, and we look forward to working with you guys in the future. Thank you.